Hello everybody, good afternoon. Before we start the video, I would just like to share with you this website for the APIs for the finite element method. So basically the idea of this is to develop modular tools for the finite element method, which include many different type of elements. So at the moment we have shell element, full integration, reduced integration solid shell element, and the full integrated solid element already available. But we are also developing more finite elements and make them available. Simultaneously, we are developing a lot of finite element templates to use with our element libraries. So you can see some of them are just free as far as you subscribe the element that you need for your FEA analysis. You can get nonlinear implicit structural dynamics analysis for free, explicit time integration scheme, buckling analysis, model analysis, multi-point constraints where you can tie different parts. So all of that for free. There are other things we also have, but we are still working on them, but they will have a small subscription fee, like return mapping procedures for plasticity, crystal plasticity, isogeometric analysis, T-splines, nerves, these kind of things, contact analysis, which is important for modeling forging, sheet metal forming, rolling, structural optimization tools as well, J-integral for fractal mechanics. Now the way it works. So if you go, for example, to the full integrated shell element, so you have some introduction to the element with some benchmark analysis and tests comparisons. We also have a pre and post processor tool where you can visualize results and build your input files to do the simulations. So you can see that this API provides the strain displacement metrics, the stiffness metrics for linear analysis, and also provides other important FEA constructs that are fundamental for nonlinear continuum mechanic analysis, like the strain stresses, rotation of the axis, internal forces, geometrical stiffness metrics, and other things. So the way it works is, so we separated the subscription for individual and academic, like PhD students, postdocs. So the idea is, if they just need to use simulation with shell elements, why should they be paying for other elements and other FEA models that they will not need? So that is the main idea of this. So you can see it's quite cheap. We also have for business subscription, so depending on the business, so 1 year £99.9 is quite, for business, is quite a cheap price, right? So solid shell as well, so very quickly, so you have a lot of benchmark tests and simulations, similar things. So we have the graphical user interface, which we developed to use these APIs, which is so basically you can import, for example, input file from Abacus and then do the boundary conditions, materials, the properties, the loadings, do everything here and run the APIs directly from this graphical user interface. Okay, you can select node sets, element sets, visualize which sets by double clicking and seeing on the tree which sets you are seeing, the boundary conditions, loading, these kind of things. You can also visualize results. So this is a full wing model run with shell elements. You can see strains, displacements, stresses, everything. Um, yeah, so please, if you are interested, so just another thing, so the site address is macinmotion.com. So we have more than 25 years experience in academia developing the finite element technology. So all of these APIs we are providing a subscription. They were extensively tested and validated, and the results are really. I can just give you a quick one for you to compare. For example, on the solid shell size, if you go, for example, here, if you see these conversion studies for this, okay, just a moment, maybe let me start with this. For this example, a twisted strip with different thickness, thin walled and thick structure. So we did run, so the API is this one, MRES API. So you can see it converges almost immediately. We compare with Abacus element, the classical one, C3D8, is very bad, but it's comprehensible because the C3D8 was not designed for bending, including bending in the 3D element. So Abacus has a better element, which is the C3D8i, the one in red. You can see it's much better behavior, but still our API still provides better results when compared with Abacus element. This is a different loading for that twist. So this is just an example to show. So we show here two of our APIs. One is the MRES, which includes bending capabilities on the element. The other is the classical 3D brick element, which is the one in black, which you can see in this example, which has a lot of bending and shear and torsion. You can see that MRES is almost perfect. AVOX C3D8i also works very well in this type of loading in this example. But you can see that C3D8 can give a very, very wrong answer, in fact, and I don't know if people are aware of this kind of situations. So this is a type of things we can provide. So just bear in mind that we are so all of these things that these finite element models for these many different problems, we have all of these implemented in Fortran. We are just basically coding this in C++, just transferring the code to C++, because C++ works better integrated with the graphical user interface, and that is and is easier to manage. Big FEA software is easier to manage software in C++ than in Fortran. So that's the reason why we are doing it. But we will soon have all of these procedures available, some for free, some for subscription, and we, of course, we provide full support on this matter. Please, if you want to reach to us, you can also go to the contact us. You have emails there at the bottom. You know now the address of the website. We'll be quite happy to discuss this with you in more detail. Thank you very much. Central difference method. So the equation of motion, okay, I'm going to put like this, for the two-body problem to be P, it's not British letter, okay, two-body problem. Right, so we already defined the rival of the governing equation, right? Differential equation, which is this one. So position vector double dot, which is deceleration, equal to minus gm over the radius, and then you have r vector dividing by the norm to get a unit vector giving the direction. As you can see, this is a differential equation you have here. It's a vector, acceleration vector, So you can have components in the x, y. I would say x, y, because we are working on the orbital plane, right? Yeah. So we are doing a two-dimensional thing. So it's going to have a x double dot, y double dot, and here you have a vector r is the position vector. So you are now more familiar with this because you have been working on GMAT and Excel for the orbit. So you know what this position vector means, right? And then this position vector, as you know, will have a component x, component y. Okay. Um, okay, so this equation here we can write in a different way. We can write this equation something like this. Just organizing things to make it more in a standard format. So if I send to the left-hand side, I get this. Right? And then if I call this, I know you're going to ask me, the flutter. This is not stiffness. It's not plunge stiffness. So this is a constant. So we can make this differential equation in this more standard form. Okay. Okay, so you can see this K is equal to Gm over R power 3. Okay.
Does it have any unit?
Sorry?
Does it have any unit or non-dimension? Okay.
No, it needs to have units because look, this is, okay, meter, right? Acceleration is meter per square second. So this needs to be 1 over square second. Right? Yeah, very quick dimensional analysis. That's what I get. Right. So now our aim is to get, okay, solve for R. Okay. That's what we want to do. Yeah, of course, you did this already. We did in the lectures, previous lectures, we did solve this analytically. Okay. That's the equation you did plot. It's the conics equation. Remember, we obtained the conics there. The one you did plot in Excel, right? The analytical solution for your orbit. We solve it analytically. Now, the idea is to solve this numerically using the central difference method. Okay. And the central difference method, so what we do is we get the velocity, which is r dot. So we're going to have these superscripts, which defines time. So we are going to do a time marching scheme, or if you want, we are going to make a loop on time, okay? A for loop in MATLAB, if you want. We are going to start, so for example, if the aircraft is at the perigee, the time starts there, 0 seconds, and then time starts advancing and while your aircraft is doing the orbit, right? So if we want to calculate the velocity at the generic time t, or the current time t, oh, I have this thing too. No, with age, I forget some things now. Just a reminder. So the velocity is given by this equation here. So it's the position vector at time step t plus 1 at the next time step minus the position vector at the previous time step t minus 1 over 2 delta t. Okay. So if you want to get maybe a a better understanding of where this equation comes from. So what you can do is you get here on the vertical coordinate the position vector r, the horizontal, the time, okay? Imagine the position of your spacecraft evolves like this with time, just a portion of that trajectory. So you can consider two time steps. For example, this one, your t minus 1, this one, your t, and this one, your t plus 1, okay? So of course, this is going to be your rt minus 1. This is going to be your rt, and this is going to be your rt plus 1, okay? You agree? So you have these points here. Now, this term rt dot, what it represents, in fact, is the tangent at time step t, tangent to the curve, right? So basically, it's this tangent, right? It's the definition of a derivative, right? It's tangent to the curve. But we are not calculating that way. So we are using the position at time step t plus 1, which is this point here. The position at time step t minus 1, which is this one here. So basically, if I connect these two, right, this slope here in green is going to be my rt plus 1 minus rt minus 1 over 2 delta t. Don't forget, delta t is the time increment between time steps, right? If we assume constant delta t's like this. So you can see if you compare this green curve with the red curve, they look parallel, right? Very similar, right? So, of course, this equation is this, yeah?
For this one, is SDR to the power of t minus 1 a problem like that one?
Sorry.
In r to the power of t minus 1, is that still a problem like the necessity of this one is straightforward? Because we had a specific thing for the t minus 1.
Yeah, we are going to have some issue here.
Here again,
This is part of, this is a central difference issue.
for every.
It's not the issue, we just need to initialization, because when our time step is 0 at the beginning of our analysis, what is r0 minus 1? Basically r minus 1. It's like, okay, I'm starting my analysis now here, okay? What is my position vector before I start my analysis? It's a bit stressful. It is a bit stressful, but we are going to see a way to calculate that for the beginning. It's only for the first time step, because in the second time step, so when t is equal to 2, when t is equal to 1 second, you have 1 minus 1, 0. So this will be your initial position, which makes physical sense. But your position at time instance minus 1, the previous one, before I start analysis, what is that, right? We are going to see a way to calculate that. That's one issue of the central difference. It's not an issue, it's just an initialization.
And this one, for example, when we go to MATLAB, we don't need a for loop for this one because it's just one thing that we need the value for. This one we
No, we always need, we need to keep track of, so when you want a time step t, you need to have the information of times of the previous one, t minus 1. Okay, so if you now go to time step t plus 1, you need the information of time step t and time step t minus 1. Right? Then if you go to t plus 2, you need information for time step t plus 1 and t. So you only need the two previous time steps. You need to store that information in the arrays. We did that yesterday, in fact. But we are going to do it today here, okay? Good work. Okay, so let me just I can leave that one, that sketch there. I think is useful. Now, this is velocity, but we need the acceleration, right? Our differential equation includes the acceleration here. So in the central difference method, the acceleration is given by this equation here. I'm going to write, so R double dot for time step t. Okay, so of course this is for the current time step we are in, so we can put subscript t here and here as well, okay, in the differential equation. So this is given by RT plus 1, position vector at time instance t plus 1, minus 2 RT plus RT minus 1 over delta t squared. Okay? This is a bit more difficult to represent in a sketch, but yeah. All right, so the next step we do now is basically I'm going to replace this RT in my acceleration R dot in my differential equation, right? And then you can see, if I do that, I will have only position vectors at different time instance, right? Different time instance, but only position vectors. So I will not have double dots, and either dots as well. Yeah, so let's do that, and then we'll come back here because there are some important conclusions I want to show you. Yeah.
So the second one, R dot impact, R dot to the power of t. This one is one velocity. Yes, is this velocity?
This is velocity. Yeah, very good. I was about to say that, but then I thought myself, okay, let's replace first, and then we can come back. Yeah, very right. So what we're going to do when we replace acceleration here, we are going to solve for RT plus 1, the new position, right? After you have RT plus 1, look at this. After you have RT plus 1, we are going to solve for this guy, right? After you have this, of course, you have this, the previous one, because I calculated in the previous time step. You replace this one here, and then you get velocity.
We're finding R to the backwards.
You go backwards, yeah. So we are going to, I wanted to replace first and then come back, but because you raised the question, but we are going to do that anyway. So we're going to solve for the position. Once you have position at time step t plus 1, you can go back to your velocity, replace here, and then this gives you what? Your spacecraft velocity, yeah? At that time instant, okay?
So then how to get acceleration?
Huh?
Or how to get acceleration?
Part of the dot.
Do you
If you want to get acceleration, yeah, you use this equation.
So you
Because you have this, you calculate this, you calculate this by, okay, I think it's better to replace it with differential equation, then you will see better, okay? Let's do that. Let's do that. So I'm going to copy to a new slide. So the differential equation here, this one in the box. Okay. So this is our differential equation, and I'm going to replace, I'm going to include this. Maybe I can add these two, same place. Okay, it's fine. Let's get these two. So I can maybe squeeze them a little bit more, otherwise we keep changing slides. Okay. So I can leave a note here. Velocity acceleration, right? Okay. Now let's replace this into our differential equation. Then if I do that, I will get r t plus 1 minus 2 rt plus r t minus 1 over delta t square plus k times rt equal to 0. Right? You can see in this last equation, the only thing I have is positions, position vector, right? Well, this is effectively, it will have an x component and a y component. So if you want, you can have two equations, right? One for x, one for y, right? But anyway, let's work with vectors now. It's only position vectors. So next step is I'm going now to solve this last equation for rt plus 1, which is the new position of my spacecraft in the next time step, yeah? So if I do that, I will get, okay, if I multiply everything by delta k square, I will get rt plus 1 minus 2rt plus rt minus 1 plus delta t square k rt equal to 0, right? I just multiply everything by delta t square. And now I just will isolate this guy. So rt plus 1 is going to be equal to 2 times the position vector at time step t minus the position vector at time step t minus 1 minus delta t square k r t. You agree? Looks so lovely. Oh, just about to pick my coffee. There's no coffee. So frustrating. How lovely and notes you're going to have, huh? Rectangles, perfect rectangle. Amazing. So look at this guys. Now, joking apart. We have here, in fact, an equation that allows me to obtain the new position of the spacecraft. That's that t plus 1 is the new position, yeah? But I need to know the position at the previous time step, t, and the position of even the previous to that previous to that previous. I don't know if this makes sense, right? This k is a constant. We already calculated this. This is the time increment. So we are almost ready to do our MATLAB thing to get this into the MATLAB, but we have only one situation. This is t minus 1, position t minus 1, this initialization. We have an issue there. And to solve that issue, what we do, okay, maybe in the slide I can write here, rt minus 1 okay, obtained from, I'm going to leave this note here, initial conditions. Okay. And what I'm going to say is, okay, so if I again plot here position vector there, time here, then you have this curve like this. So we are going to consider now two time steps. This one, t minus 1, So this is going to be my RT minus 1. And this time step here, T, okay? So this is delta T. And this is going to be my position vector times step T, okay? This one is a little bit strange. And sad. So what I'm going to do is, I'm going to get my velocity by getting the slope. So basically so what I mean is that I'm going to get my R dot T by doing the RT minus RT minus 1 over delta T. Okay, this is different from the velocity we obtained from the central difference method. This one here, right? Compare this, is different, right? So in one I just did, I'm using the point at time, the position at time instance T minus T minus 1, and here's only delta T, it's not 2 delta T, right? So the central difference method, this is the right formula, but I'm using a different one only for this initialization thing, for this RT minus 1. We are going to need these only for the initial time step. The other time steps, we don't use this. It's only for the very, very beginning of the loop in time, okay? So basically then you are going to have your R dot T equal to RT minus 1 over delta T. And then what I'm going to do is I'm going to say, okay, for T equal to 0 seconds, I'm going to have R dot 0. What is R dot 0? Huh? No, this is not power 0. This is just a superscript. It's not an exponent. This is time 0, beginning of analysis. What is R dot at the beginning of analysis? Initial velocity, right? So if I replace in this equation T by 0, I get on the left side initial velocity. On the right side, R0 is initial position, right? Which we know. Minus R T minus 1 is our unknown, what we want to calculate, and delta T, we know. So from this equation, I can say that my here is not T minus 1, it's 0 minus 1, right? So it's minus 1. Agree? So my R minus 1 is going to be equal to R0 minus delta T R dot 0. Right? Look, I just need to do this one time before I start my loop in time. Then I calculate my R minus 1. Remember, I told you this, R minus 1 doesn't make sense, right? So this is just a mathematical manipulation to initialize our loop in time. So we can start the loop. Because on the next time steps, I don't need to do this anymore. The next time steps in the loop. This is the equation. So in time step, okay, 0 seconds, but for example, imagine the next time step is 1 second. Imagine delta T is equal to 1. You are going to have to calculate the position vector at time 2, next time step. You will need to have position vector at time 1, which you calculated.
And position vector at time 0 is your initial configuration or initial position of the aircraft, right? And then you keep going in the loop. You need to update these vectors, of course. Every iteration in the loop, you need to update this vector and to see it. Okay? Right? So I'm going to switch to MATLAB, but before I do that, I need to get these equations because I don't want to be switching from iPad to PC all the time. So let me see. Let me make a screenshot. So let me make a screenshot of this one. Oh, no, not, yeah, this one, because there is K there. Okay, a screenshot of this guy. And now let me send this to myself. And I think I'm pushing Microsoft too hard. You know what happens when I push Microsoft too hard? It crashes, right? Okay, this one is done. Was sent, so I don't need to store this. Let me now do a screenshot. Yeah, this one is important because we have all these equations, right? We need to get into MATLAB. Okay. Okay, share to myself. Okay. And I think, what else do you need? Maybe this one for the initial, for the R-1, right? Let's get this one as well. And I don't think we need any more. Okay. Let me just see if they arrive here somewhere. Where is this guy? Oh, okay. Yeah, they are here. It's amazing. I'm surprised with Microsoft. Right. Download. Okay. So this is downloaded. This one, download. Download. And last one, upload, right? Okay. Let me see. Where can I get this thing? Right. Just a moment, guys. Let me see where I can put this thing. Oh, right. Not that bad, Microsoft. Edit with photo. Okay, I have all of them here. So I think I'm ready to switch. Okay, so let's do like this. Let me share screen here. Share. Yeah, share this screen. It didn't share, right? Because it stopped share that one. Yeah, that's why. Now it's sharing screen. You can see the screen, right? Okay. Oh, come on. Why is it so small?
That's what.
Oh, really? Okay, it's fine. We can do like this. Uh, okay. Let me create a new folder here just to organize these things a little bit better. Um, where do you have desktop on this thing? Okay, it's here. So let me create a new folder. So let's put the name of the model here. 5667. Right. And then we can, okay, right.
But you want to use Simulab as well.
Which one?
Simulab.
Simulab.
Yeah.
Looks very sophisticated to me.
Oh, you haven't used that.
You have to use?
No, I'm saying you haven't used that.
No. That is more for
Then,
control dynamic robotics, right? These kind of things, rigid body rotation thing. Yes. It's not real my thing, you know what I mean?
Yeah.
Okay, you can see the MATLAB thing, right? Okay, good. So let's start. Let's implement here a program. So let's create a new script eventually. So let's do clear CSC. Was clear CSC
yes, it's CS.
and CLS.
CLS and CS.
Close one, CS.
Okay. So let's let's give a name to this thing. Central difference method. And for the 2BP, two body problem, okay? Right, so we have our file here. So I created a folder here, so we'll have our files in this folder. Okay, good. So what do we need to do? So let's initialize these variables here. So let's create this GM variable. Okay, what is the GM? You guys have there 3.9? 3.9?
986.
986? 3986?
Yes, 3986 times 10 to the power of 14.
14, right? Okay. So we have GM, define this variable with this value here. What else are we going to need? R, okay. So yeah, R. R is the distance of the satellite, right? Which one is in your sign? 50,000 kilometers. 50,000 1, 2, 3 kilometers. Let's put 3 more zeros for meters, right? Okay, now with these numbers, we can calculate our K, which is GM variable dividing by R over 3, right? Okay. So we have all of this. Now let me bring here this one. It's a bit tiny, but I think it's enough for us to. I can do is. It doesn't. It's not worth taking more than this. It's not going. Oh, maybe it goes if I. Yeah. Okay. It's better, right? You can see better. God, it's so hot here. Let me just open the window. Do you mind open a little bit that window? So everything is closed. Yeah, thank you. Right, so let's do the R minus 1 first. Okay. What is this? Oh, I don't want this. This.
The initial tangential velocity.
Sorry?
And there is no need to have the initial tangential velocity, because for example, in case we have here, you don't need it for such a transmitted. Because it was given.
You need is this R dot 0 that you have there.
Also, you want we can take that.
Yeah. Well, yeah, I gave that, right?
Yeah, it's given.
Okay, let's do that. So let's write a variable like this. Initial.
Because in free tangential velocity at every axis.
Yeah. How much was that?
3,000 meters per second.
3,000. So 3,000. So we define R as meters. So yeah, this is meter per second. Okay, it's fine. Initial velocity. So this is going to be our R dot 0, right? Let's group this thing together here. Now, our R0. Okay, so so what I suggest is we work this for X and Y components. So it's the same equations, but instead of working with R vector, we work component by component, right? So this thing, in fact, yeah, so let's say our X underscore 0. So this is my R0 is going to be, I'm going to say is going to be equal to R, right? The periapsis, yeah? My Y0, my initial equal to 0, right? You agree? Huh? So I'm using this equation you have here, right? So I need to have, to calculate my R minus 1, I need to have X0, my initial X coordinates at the beginning of the analysis, and the velocity X dot.
So you said X0.
So this 0 is time 0, time equal to t equal to 0 is the beginning of the analysis, right? This is not an exponent. Don't think like this, okay, this is r exponent 0, so result is 1. No, that is wrong. That's not what I'm saying, okay? So these superscripts I have here, they are associated with time step. So this is the position vector at time step 0 is my initial position of my aircraft, right? So this r vector is a vector with an x and y component. So it's my initial x position of the aircraft and y position of the aircraft. That's why I'm separating here x and y, okay? So if you think on perigee, your aircraft starts at perigee, your x is going to be equal to r, the 50,000 kilometers, but your y is 0, right? At the perigee, right?
Yes.
So that's why I put 0 here, yeah? Now, in terms of initial velocities, let's say Vx is the x component of velocity at time step 0. So the aircraft at perigee, the velocity is in the x direction or in the y direction? Y, right? You know that, I can see you have been working on your assignment. So the x component of velocity should be 0, right? So 0. And the y component equal to the initial velocity we defined there. Right? And then now we are in condition to calculate So let's put some comments. R R minus 1. Okay, we are going to go to use this formula you have there on the screen in the red box. So I'm going to say that my x underscore r minus 1, okay, x r minus 1, something like that, is going to be equal, so it is what I have on the left-hand side, equal to my initial position x underscore 0 minus, okay, delta t is something we should define. Delta underscore t. Let's make small time steps like, okay, let's say 0.1 seconds. Okay. So minus delta t. I'm just inputting in MATLAB this equation in the red box, okay? Times the initial velocity in the x direction, which is Vx underscore 0. Okay? Now the y component, I can just copy paste this one and change. I can say y, r minus 1 is going to be equal to y0, vy0, right? Agree?
R into X and Y.
Hmm?
You are decomposing R into X and Y.
Yes. Yeah. So basically we are going to have two differential equations, one in x, the other in y. Okay? Okay, so, right. Go away. Oh. Now, what do we have to do? So this minus 1 here, okay, this RT, okay, so let me initialize my R. Okay, sorry, let me be more consistent with my labeling. It's not R minus 1, it's T minus 1. R replace t minus 1, okay? Just for reading better the code in the future, if you want. Now, what I'm going to do is, you can see in this equation here, in the blue rectangle, so RT minus 1 is sorted, but I need RT, right? Let me put here also T minus 1. Now, T. So I'm going to say X underscore T is going to be equal to my R, right? So this is is equal to X0, right? X0. This is before we get into the loop. Score T is going to be equal to Y0. Okay? And now, yes, now we are going to start the loop. Start the loop in time. Time marching scheme, okay? We are going to start our loop in time to start getting our orbit. Yeah, yeah.
T1, could you show where that's represented in the equation?
Which one?
The T,
T
like the XT and
Oh.
T.
is this. And this. So T minus 1. Okay, I can do it with mouse. So T minus 1. This is this one. Okay. Now we need to do RT and RT, which I call X underscore T and Y underscore T. Okay. Right. Now, if we do something like this, for T, which is our time, I'm going to start a loop from, well, T starts in 0, and it goes in increments of delta T. And there's one thing we need to define: total time of analysis, okay? Total time. Okay, let's say you want to do a 100 seconds analysis, okay? Then you put here total time. So I don't know if you are familiar with what this format you have here. I just underline in blue represents, but yeah.
0.02 delta in the time
Let me-
step of total time.
Yeah, let me zoom in this a bit better because it's so tiny there on. I think it's that, right? So basically, what this command here in MATLAB does is, the first one before the column is 0.0 is initial time. 0 seconds. We start from 0, okay? The last one, the total time, is the total time, the total length of your analysis, right? In terms of time. So this is going to be a iterative loop where this t is going to increase each iteration by an amount defined by this delta t in the middle. So first time step, t is equal to 0. Second time step, t is going to be equal to delta t. Third time step, t equal to 2 times delta t, and so on. Right? That's what this thing means. Hey, now what are we going to do? Well, we are just going to plot our equation here, this equation here, right? So I'm going to say something like this. Look, x underscore t plus 1, which is what I have on the left side of that formula at the bottom, right, is the coordinate x of my spacecraft at time step t plus 1 is going to be equal to 2 times my coordinate x underscore t, which in the first time step will have this value, right? Minus x underscore t minus 1, which at the beginning will have this value, minus delta t squared. So I will multiply by delta t again. I prefer to do that instead of the exponent. Times k, which is somewhere with that one k, right? It's k times x underscore t, right? And then for the other one, we can just copy this and change x to y. Yeah, okay, I'm teaching you lazy stuff. Okay, so ignore this bit, okay? This is usually when we have our mistakes. You know, rush is enemy of perfection, right? So it's good to do a double check. Yeah, it seems okay, right? Okay, after doing this, what do we have to do? We need to prepare these variables for the next time step. So what I'm saying is that my x t minus 1 is going to be equal to my x underscore t. Same thing for y. Right? And maybe leave a line in space. My x underscore t is going to be now updated with my x underscore t plus 1, the one we just calculated. The one we just calculated in t plus 1 is going to be my t for the next time step.
So in doing this, you're solving that problem, the central method of having t minus 1 before.
Yeah, you don't need to do you don't need to do this anymore. We only did this t minus 1 one time before the loop for the initialization. Now inside the loop, you don't do this anymore. You just update t minus 1 like this, right? Of course, you have to do the same for the y direction. So right. And then you can see in the next iteration, what is going to see, you are going to have new xt and new xt minus 1. And then you will calculate a new TP minus plus 1, which you'll then update these variables again and continue the loops. Tick, 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 tick. Yeah? Okay.
In loop until it gets to 100.
Hmm?
When it gets to 100, you'll stop.
We will define the stop in a later. That there's something that I want to do before that. So we are going to see how we can get the orbit period from this loop. I ask in your assignment, right? Well, the reason I'm safe to do this because in your that's why I asked Runge. So I'm completely happy to do this thing here in MATLAB. We do a kind of a tutorial for the central difference method. You just now in your assignment you need to be able to transport these concepts to the Runge. Should not be too much difficult, right? Now there is one thing I want to do here because what we have so far in this group is the position of spacecraft, but I can also calculate the velocity of spacecraft, right? Oh, another thing. Okay, that's another, before we go to velocity, there's an important thing, because look, these are not arrays, vectors. So what happens is, I'm replacing, for example, x t plus 1. I'm replacing this variable at every iteration, right? I'm not saving the values for each time step. So at the end of the loop, if you want to plot your orbit, you need to have all the values, right? For X and Y. So we need to save this in arrays, yeah?
But the orbit trajectory, right?
Huh?
To plot the orbit trajectory by MATLAB.
Sorry?
To plot the orbit trajectory.
Mm-hmm. Yeah. So what can we do? So we need to store these things, yeah, to get orbit trajectory, like you said. What is this? Go away. Okay. Okay, so let's do something like this. Let's store this initial position. Okay. Array to save the spacecraft position at every time step, okay? So these comments, they are helpful, especially if you are picking this in the future. By the way, let me, just for curiosity, see if there is any ghost check-in on SIDS. Sorry about that. I don't know why it's asking me. I was logged in, it's asking me this again. Yeah, let me check this because Oop, okay. So teaching events. Okay. Okay. All good. All right. Sorry about that. So let's create here. Okay, so let's create one array with, okay, I'm going to call it epoch because you guys have this in GMAT, right? So let's make this a NASA competitor software, yeah? Epoch zeros. So let's create one array. In fact, what we can do, we can divide the total time here. Okay, we can put total steps is going to be, I don't know if this is correct in MATLAB, in 16, yeah, should be fine. So I'm going to divide the total time with delta t. It's just if it is 16 bits or 32 bits, for an integer is fine. I think it's that, but anyway, we'll see. Usually if the things are not what we think they are, what happens is the codes, they just explode or crash. Or we'll see very soon once we debug, okay? We are going to do that. Okay, so basically I'm saying, okay, I want to store all this information in a vector or in an array, but I need to know the size of that array, right? So I need to know how many time steps I will have. So my idea is, okay, I have the total time. I have the incremental time. So if I divide total time by incremental time, that should give me the number of steps, right? Make sense? Imagine total time is 1 second. Delta t is 0.5. Number of steps, 2. Yeah? So I have these total steps. So then I can put here total steps. So this epoch, what it's going to store is my time. It's a kind of timestamp. Epoch, timestamp. Now, x x coordinate, x coord is going to be zeros. So I'm creating an array and initializing it. Total steps. And same thing for the y coordinate. You can give different names here. Total steps, right? Okay. And now what I'm going to do, I'm going to save the first one. The first one, so x coord in position 1 is going to be equal to my x 0 initial. My y coord in position 1, the first position, right, in the array is going to be my y 0. Make sense? It doesn't make sense. Oh, you lost. Okay. Right. So let me just do a save. Here in the for loop is fine, right? Okay. For loop is now this arrays I just created here. So basically my aim is going to be this xtp1 and ytp1 I calculate for every time step inside the loop. I want to store this information in this array because at the moment I am not storing, I'm not saving it. I'm just replacing. So for example, iteration 0, I calculate TP1, xTP1, yTP1. Iteration 1, I replace xTP1 with 1 in iteration 1. Iteration 2, I replace, right? So at the end of this loop, you will have only a position for the last time step of your loop. You will not have the history of the position of your error. That's why I'm creating these arrays. Okay, so that I am storing everything. And of course, you need to store stuff here now, right? So I propose storing here inside the loop. So let's put a comment here. Save time and x, y coordinates. Okay, so I'm going to save this. I'm going to start with time. So my array epoch. Oh. Okay, hold on. Let me just check one thing here. I think yeah, I think this beginning of my analysis should not be 0, should be, because we did the 0 here, right? We did the 0 here. This should be delta t, I think, my initial one. Yeah, and now I can say, oh, no, it's okay. No, it's okay. It's okay. Sorry. Okay, just hold on then. Okay, I need, oh, okay, I know, okay. I need to have a counter. Okay, let me do one thing here. Let's say, create a variable count. Okay, counter. equal to 1. Okay. Oh. This epoch thing is okay. I think I was right. This should be delta t, delta underscore t. We still need to have this counter 1, so it's fine. Counter. Same thing here, counter. And now, now I'm going to say here, I'm going to increment my counter. Counter. Does it work in MATLAB? No. Equal to counter plus 1. So I increment my counter. So my counter now is going to be 2 in the, and then my epoch counter. Sorry,
Post counter.
it's a counter.
Yeah, pounds.
Yeah. So basically what I'm doing is I start my counter with, I start with 1 in this case. And then inside the loop, when I increment by 1 for every iteration, increment the counter by 1. So first iteration, counter is incremented to 2, then to 3, 4, 5, 8. So I can go into the indexes of the arrays.
Why don't we use like for I in range? Like can't I do that? You know when you
Yeah,
use
you can do it in a different way, yeah. But that is too advanced for my MATLAB skills, I think. Yeah, you can do that way. You can do in your coursework, you are free to do whatever the way. Okay, I think I'm not being very smart, to be honest. Let me just, okay, hold on a sec. Let me just try different attempts here. So maybe I should update this guy before this, let's see. So I don't update counter yet. So what I'm going to do is this epoch thing. Okay, now I can have back my 0 initial time step, which should be. And now counter is going to be equal to 1. And okay, it looks like it's okay now. So I'm going to drop the time t, which first one should be 0. My x coord for my counter should be equal to my xt. Okay, my y coord counter should be equal to my yt, right? That's it. And now I increment counter for the next iteration. I think this will work, right? See, guys. Well, let's see if this works. Let's do some kind of debug ourselves. So I initialize the arrays here, counter equal to 1, so and I go into the loop, right? So counter is going to be 1. So epoch in position 1 is going to be equal to my time, which is 0 in the first iteration. Yeah. My x coordinate is going to be equal to xt, which for my first iteration is going to be equal to x0, upstairs, above. Y coordinate equal to yt, which is going to be y0. And then counter is going to be equal to 2, but then I go to the next iteration. My t is going to be equal to delta t, counter equal to 2, right? So I will store in position 2 my time t, which is delta t. My x coordinate xt was updated here with t plus 1 at the bottom. I think it's working now, right? Should be working, but we'll see. Before we test all these things, there's one more thing I want to do here, and I think you should do, which is velocities of spacecraft. You want also to track velocity of the aircraft for every time stand, right? So we need to include velocity here.
I'm sorry, the time period, I think we did. Time period. You mentioned time.
We still have to do it. So what I propose may be, I can see this might take a bit longer than I was expecting. Let's do a 10 minutes break. We do one break today because I suspect we might not have time for the propulsion. So let's do a break now. And we come back. So we come back at in 10 minutes at 10:37, okay? Right? We continue from there.
You can get that from the
Yes.